Well, hello everybody, and welcome to the next installment in our tutorial video series on programming for the TurboGrafx and PC Engine. Today is going to be all about graphics and getting things on screen, actual bitmap graphics. It's going to be a pretty long video, so I've split it up into two parts. I hope you'll enjoy watching both parts. I'll just give a very quick rundown, and here's a quick diagram of what we need to do. First of all, we need to make some graphics and then include them in the ROM. We should set up some VRAM constants and some variables so that we don't always just write magic numbers to the graphics hardware. The constants will mean something to us. Next, we will try to load the graphics from ROM into VRAM. We will write our own routine first, and then we will use the magic kit include files. We will make some macros or steal them from Magic Kit. So the final three things are getting some text and hex readout on screen. After that, some background graphics tiles, which have a splash of color. And then finally, we will have some sprites, movable objects drawn on screen. And then in a further video, we can place them and move them around. So this is our plan for today. Okay, so let's continue where we left off. You'll see that I changed the text in my text editor just to make it a bit clearer and easier to see in the video. Anyway, I've added some comments just where we left off before we had a single hsync moving on screen. Remember, it looked like this. Our code set up screen dimensions and made an hsync interrupt travel down the screen and change the colors at the border and in the background whenever that happened. And that's what our code does. It starts up and changes the border colors and background colors. So you'll notice that the only change I've made between this and the last video was I've moved the background and border color changes into macros. I've changed them to macros to make it a lot more compact. So you can see I've moved those into a macro file, changed the background color to green, changed the cyan, dark green, changed the borders, dark blue, blue, red, and white here, so we can hide that dirty, messy code away. And if you remember our vsync code, change the border color to red and then back to blue after waiting a while, so we can see where the vsync interrupt triggers. Then it sets up the hsync interrupt once per frame. And when the hsync interrupt triggers, it changes the border and background color, and it turns off in hsync interrupts for the next until the next frame. And that's our code. It's pretty short for now. Well, right now our simple code just makes an hsync interrupt travel down the screen once and then disappear. I wanted to make that a bit more dynamic so that it goes down the screen and then comes back up again. So let's have it ping pong up and down. Now to do that, we'll need a new variable called direction. And I also make one called vblank count, and most games and demos have a counter just for each frame, for each vblank that triggers to make timing. So if you read this counter, you can see how many vblanks have elapsed, and you can skip odd or every fourth or every eighth, whichever number of vblanks, to slow down your code a little bit, to slow down some on-screen effect. So that's what I will do here. Alright, so main code, we'll clear that direction variable. I'm going to change this just from 0 to the first scan line on the screen, or in the active area, just so we're not waiting for it to start. Okay. Okay, in our vsync, let's see, what do? We set the border color to red, wait a little bit, change it to blue, Okay, and here. Maybe I'll change the background color back to green. Okay. In the VXM code, we need to increase our VB count as well. Okay, that'll increment it every time, every V blank on screen. It'll increment it once. Okay. Okay, and in the H-sync, what I'm going to do, I'm not going to have it reset the background and border color. I'm going to make it dark blue. And hopefully that'll work okay. The background will be dark green. Let's save that and see what it looks like. Okay, so you can see the change a bit more clearly there. Next, the ping pong effect. We'll go back up to the V-sync routine, and we've increased the V blank count here, and we're going to use that V blank counter. First, to slow it down. Branch of bits 0 is set of VB count to no move. Let's not move the line. Okay, oops, comma, there we go. So for every odd or alternate V blank, we're not going to do any changes. We're not going to make any changes. Okay? That will slow down the screen movement by half. So make it easier to spot on video and analyze as well. Next thing, it doesn't matter what we're going to do, but we have our direction variable up here. And to do a ping pong effect, you got to, go down the screen and then change that direction variable, and then go up the screen and then change it again. So it doesn't matter which one we do, but we'll have BBS 7. Okay, so if the direction is negative, it'll decrement the line counter. It'll go up the screen, basically. So that'll be some code to fill in later. Here, okay. But for now, what we're going to do, okay, we're going to move this here, okay. So we're going to increment the line as normal if the direction is 0. Okay, and then decline, we're going to decrement that right here. Okay. All right, and then up at the top, we're going to make some constants, just so we don't have to fiddle with numbers in the middle of our code. Okay, so I guess I'll put that here. What are the constants for the top line? So interrupts actually start at 0040, but I'll set it to a bit earlier so you can see it actually start. And bottom line, well, that's 240 scan lines plus 0040 hex. I'm going to go crazy and make it hex 150 for our bottom line. Okay, so this will be a hard-coded start and stop, or a limit for our scanline interrupt. Okay. So right now in the middle of my screen here, I have the code that will change the direction up and down. Okay. So So we increase the scan line, and we'll also compare to see if it should change direction. Compare a constant with hsync line. Just copy this guy again. Copy, paste. Okay. And if it's not equal to our what we compare to, we'll just go to the end of our line. We've moved the line right here. It's the same place as no move, actually. Okay, if that's true, we'll flip or negate the direction. We can just decrement that. That's not diction. Okay, we'll negate the direction just by doing decrement. And we'll get out of here. There we go. Alright, so that's our code here. Increase scan line position. That's what we're doing here, and then down here we're decreasing. Okay, so we'll do a similar compare. So if it's going up the screen, if it's decrementing from this branch right here, it'll go up to the top of the screen, and we need to check and see if it hits the top of the screen. So I'll compare those two, the top line constant. All right, and I think I'll just borrow this code again. Okay, compare it. If it doesn't, we'll just skip over it. Otherwise, we will increment the direction, so it flips it again, it resets it. There we go. So that is our scanline moving code in our vsync routine. So let's check to see what we've done here. Save that, assemble it. And, okay, so we have our line going slowly down the screen. And slowly back up again. Now let's look here. When this scan line goes back up to the top of the screen, you can see that darkness disappears, so interrupts will not trigger above that point on the screen. And watch it go down, it'll trigger past the V blank and wrap to the top of the screen again. So we can see from this demonstration that between values 0, 0 and 3f, there's no hsync interrupts. In other words, that's an invalid area for hsync interrupts. They will never trigger, depending on the screen setup. But I'll reset that. When our hsync interrupts go past the V blank position, which is whatever you send it to, it'll continue and then wrap to the very top of the screen, up to the very end of that border area. So the top border area is actually past V blank, and it's actually a very high hsync value. So the raster, active raster 0 basically, is the top of the active background area, and that'll go all the way to the bottom of the screen, and then we'll wrap around to the top. So if you actually want some kind of scanline effects at the top of the screen, you've got to set that to happen way past V blank. We can check what raster position that is, but as you can see up in our code here, I've set our bottom line to 0, 1, 50, so around 0, 1, 40 or 30 or whatever, you can actually see that hsync interrupt trigger at the top of the screen. Okay, So the top of the screen is actually a very late extended H-sync past the V-blank. And that's what this slow-moving colorful H-sync tutorial was meant to show. Just where do H-sync interrupts happen on screen in relation to the actual V-blank time. Okay? Okay, let's get some actual graphics on in our demo now, once and for all. So I'm gonna load up some kind of ASCII font and just some background graphics and some sprite graphics, just as a sample. So, well, here, you probably already know what ASCII is, but here's a table of bytes from hex 00 to all the way to FF. And this is, you can call it an ASCII table because you can see, starting in around ASCII 20, there's a space, exclamation mark, quotations, and then it runs through numbers, and then capital letters, then lowercase letters, and so on and so on. So if you make a font for your demo, you usually probably want to have the letters and numbers at least match up to the ASCII alphabet. Otherwise you'd have to move your data bytes around if you include text. So first of all, I've taken, well, an example font from a shooting game, and you can see the first line is hex 00, and then hex 10 is the second line, and that's actually just a font for a hex readout. And then from 20 is space, an exclamation mark, and so on. Then the numbers, then ASCII uppercase letters, and that's all I have. That's all we need for now, just for a simple demonstration readout. Alright, and this actually uses only 3 different colors, so I have it saved as a PCX file with a very simple palette of black, red for a shadow, and then yellow for a highlight, and that's all. That's it. I've also really quickly made some background graphics. I just snapshotted them from Bonk's Revenge. And again, this is just a 16 color PCX file. It's 128 by 128 pixels. So this will fit into a single 8K bank on the PC Engine in the ROM and in a VRAM page, if you want to call it a page, 8K VRAM page. So it means it's easy to set up and address. And then I also have a sprite, 2 sprites here. Pong and then a Chikun. Each of them is 32 by 32 pixels wide and tall, and the green is a transparent color, and then the other pixels are going to be overlaid on top or behind of the background. And you can see this only uses 16 colors, even less. We will deal with more colors in one screen a little bit later. Okay, so right now our assembly file is only 8K, makes up 8K of code, and when we add our graphics we're going to have to expand that to 16, 32K, etc. So, to do that, well, maybe I'll start with the font. The font is only 128 by 64 pixels, and so at the very bottom of our code, I'll make some spaces here, and then set up a new bank. The bank actually starts at bank 0, and I'm going to make these graphics go to bank 2 and 3, so that's right before the next 32K boundary. I'll make the graphics load in at 4000 in CPU space, so we can bank them all in the same place. Alright, and then we do inc chr, and then, well, I'll copy and paste the location. Parafont.pcx. I'll just assemble this and see what happens. Yeah, so there at bank 2 we have another 4K of data that gets loaded in, and that's our font. So I will do the same thing with the background tiles. And I'll copy and paste the name. Alright, that's a Pong BG, Pong background. And this will take up a full 8K of graphics actually, so we don't need to type anything. We're going to be including everything. If we were including only a section of the graphics, or of the image, you would have to write the origin of where you get the graphics from, X and Y coordinates to start, in number of pixels, and then the number of tiles you want to copy over, like for example, only 10 tiles and 12 tiles across and down. But we're doing the full 128 pixels, so we could type it like this, 16 by 16, because 16 by 6 times 16 times 8 by 8 characters is 128 by 128 image. But we don't need that here. And this is 128 by 128 image, that's one whole bank, but this is only half a bank, so we can fit our sprite graphics in here as well as palettes and stuff. So actually right after our font I'm going to include the sprite graphics. Oops, didn't type that in. So inc.chr means include character graphics, in other words background tiles, and then inc.spr means include sprite graphics, sprite tiles, because they use a different graphics format. Okay, so let's assemble this and see what we get. Okay, so as expected, our bank 2 has more than 4K of code of graphics now. It's got the font, background graphics, and sprite tiles, and then bank 3 uses up the whole 8K for that bonk background, and so it's a 32K ROM now. So if we run it, so well, it's the same ROM as before. Let's look in VRAM. Well, as you can see, there's nothing in VRAM, so this might surprise you. On other 8-bit systems like the Commodore 64 or the NES, on the Commodore 64, the OS loads in the graphic characters for you already, so all you have to do is write to the screen memory and you can get letters and words appear on screen. So that does that dirty work for you. And on the NES, on the 8-bit Nintendo, if you have character graphics in ROM, those will automatically appear to the PPU, and so those will show up on screen automatically. But on systems like the PC Engine or the Super Famicom, Super Nintendo, you have to do all the loading of graphics into VRAM manually. You have to do it all by yourself. And so there is that extra step or extra couple of steps to get done first. So yeah, that's why it's a little bit harder than the NES. But we have to learn that and get used to it. But right before we fix up our program or get going with loading graphics, let's load up a video game tile editor. Here's the familiar YYCHR. This will let you view character graphics inside of Famicom, Mega Drive, Super Famicom, etc. games. So if we load our tutorial into that, we can see what our ROM looks like. This is our code, this is our starting code. Actually, let's set it to 4 bits per pixel SNES. That's the same background format as the PC Engine. Okay, so yeah, here you can see this is our startup. This is actually our game, our main code, and this is the startup code here. It's seen graphically. bank 1 is empty, bank 2 has our font, as you can see, and our sprites are here. But they are unfortunately in a different graphics format. You can't really view them in most editors. And then finally, well, here's that bonk background. It takes up the all of bank 3. The palette is wonky, but this is the default one for the hex editor, or for YYCHR. But at least you can see that those have been loaded in to our ROM correctly. So what do we do? Well, first, in our macro file, I've made a couple of new macros down here that will turn off the screen and interrupts while we're loading our graphics. And this will be necessary so that our VSync or HSync interrupts don't trigger and cancel out our graphic loading. So here I've made one called ints off, just that turns off the screen and turns off all interrupts. And here's screen off. Interrupts are kept on, but the screen is blanked. And screen on turns everything on, and background on, so background only. So we'll use that in our main code. Oops. Okay, so ints off. I'll disable all interrupts while we load things. And so, you can see there's also a macro up at the top called map, and that's very helpful. As the comments say here, it'll map a memory bank into memory just by using its label. So, let's see. Let's start with the bonk background as an example. So we get its label. So in our main code, let's say right here, map bonk background, so that will map in ROM bank 3 into the 4000 and up space in the CPU. Okay, so next we have to load our graphics. What does that look like? Well, it'll take a lot of code. So I'll show you it once, but then we're going to have to put that into a library and just call it in a subroutine. That'll make it much easier. So first we have to set up VRAM, the correct VRAM address for writing to VRAM. So let's see, I think we're going to have VRAM address 2000 be where our bonk background graphics are going to start. So let's first store that in the temporary variable di. Write to register 00. Doesn't matter if it's hex or not, but so first we set up register 00. Then we store what's in DI to video data. That's the address, or the registers that'll set up the address, which is register 00, and that loads the address of 2000 into that address for writing. But now we have to set it to actually enable writing, so you set vregister 02, and now that will receive any data that will come in and put it into VRAM at the specified address of 2000. So this is the first step. Next we have to make a loop to copy the graphics manually from our ROM to VRAM. So we'll copy our graphics, which is called bonk, or the BG, that's the address, to SI the source. So this is copying the value of the address of bonk BG, so it's the location, and storing it in our variable SI, the source. We'll call it ROM graphics there. And then next we'll specify the size of words or data to write. And so this is a full, let's see, 8K of graphics, which means hex 2000 bytes. But this is a 16-bit system, so it doesn't work in bytes, it works in words, 16-bit words. So hex 2000 bytes is 1000 words. I'll store that in CX, another variable, and I'll comment 1000 words. Then I'll set up a loop. So we're using the usual load and indirect indexed transfer using the Y register from this source 0-page variable. So load a byte, store it in video data, and I'll copy this. Oops. Increase Y, increment Y, load it again, and this time save it into the high byte, because it's 16-bit register. Remember, video graphics, the video registers and video chip on the PC Engine are all 16-bit. So 16-bit video register. Okay. If Y overflows back to 0, 0, we have to increment SI plus 1. Exactly as I say. There we go. So that's not commenting. So we'll decrement the number of words to write. And after we decrement the number of words, we'll check to see if it's gone down to 0. So we load the low byte, or it with the high byte. So CX low and CX high, and that should check if that 16-bit size variable is 0 or not. And then if it's not 0, we'll branch back to the beginning of the loop and load 2 more bytes, and so on and so on. And one last thing to do, remember we have turned off all interrupts in the screen, so we need to turn them on at the end of everything. So we'll set the background color to green, the border color to blue, and then using that macro, screen on. Let's see if it works. Alright, no change here. So this still works. Look at VRAM at 2000, and here it is. Here are the graphics. So we've loaded up 8K of graphics from our ROM into VRAM. And we'll do the same thing with the font. But doing all this code just each time we do it is a bit wasteful, so we will put this into a subroutine that we can call, and all we have to do is write to SI, CX, and DI. So the source address, destination address, and size, and then have our subroutine handle that. So that'll save us some time. And ROM space, of course. Okay, so to get graphics loaded more simply into our into VRAM, we're going to poach from Magikit's old libraries. And so here there's two files named library.asm and library.inc. And ASM has the assembly subroutines, and inc has a bunch of macros. So let's look at what they have. So we'll look at library.inc. So these macros are simple one-line setups. So set VRAM address for reading, VRAM read address to a certain address, or set VRAM write address to an address. So you can put the literal address in those macros. Here we'll be using this, set a background palette. So we point to our data in ROM which has the palette, and which palette index to start from, or sub-palette as it says here, 0 to 15, and then how many sub-palettes or palettes to write in. And so with sprite palettes as well. So this will load up an entire 16 color chunk of colors palette in entries by index. So palettes are indexed 0 to 15. And then the size of the palette to write is also 0 to 15. So I'll do 16 colors at a time. If you want to do one color at a time, you can do set color. So the index from, I think it's 0 to 512, isn't it? And then each RGB value. So you can set single colors if you want. Here we'll be using this a lot, a vload macro. It'll write from ROM, on a ROM address, into a VRAM address, which might be optional, and size, how many words. And you'll note here I've written, there we go. I've written in my comments already. This used to say store word /3cx. Anyway, they forgot the hash tag or $sign, or sorry, the number sign here to load a literal value into cx. It was loading an address, so I think that's probably an error. So I wrote my comment there. And here's where you can copy a BAT, a tile map into VRAM, and it actually lets you have a small BAT file and load it into the proper size width and height of the actual BAT in VRAM. So it'll skip, 32 words or 64 words, depending on, you could call it the stride of the VRAM BAT width and height. And this also copies a default font into VRAM, but I'm not going to use this actually, so I've taken a couple things out of there. So maybe we'll go away and in the include directory put in a little bit tiny cut down library.asm and library.inc file already. So set VRAM address, set background pal, sprite pal, set color, vload, bat copy, those ones only. And their corresponding assembly files in the library.asm. Set palette, load bat, load VRAM. So as you can see, most of these library subroutines take those 16-bit pseudo variables or pseudo registers as input, and it has an explanation here. Load VRAM, memory location. So this is what I did. This is what I typed out in our tutorial file down here, just to go through the motions one time. But from now on, we're going to load everything using macros, and we will include these library files as well. Alright, so in order to get these libraries included, we'll have to modify our startup.asm program as well, or assembly file. And include, and I've got the name here already, include library ASM. It's called inc. There. So where we include our equates and macros, we'll also include this library. And because this library takes up some machine code space, we'll need to probably expand where our startup origin begins. So probably FE00 is a safe place. Alright, so let's assemble that and see what it does. Hopefully no errors. Yeah, no errors. Our code starts at E00. Oh, sorry. Our startup code starts at FE00, and the libraries take up space to FF5E. And then there's a bit of space from there to FFF6. So yeah, we needed to expand at least the startup location here to make room for libraries. And if we add more pre-made libraries, we'll have to change that as well. But at least it's a way to separate our main code and our startup code. So let's look in library.inc at the vload, the VRAM load macro, and we'll just use that. Here it is down here. So vload, you write the starting VRAM address, the data address in the ROM, and then the size of words to copy. It says here, number of words to copy, so it's explained already. And my comments are there still. So vload. So I think I'll close this. So let's get rid of all this. We map the bonk background, and then we don't need to set up the VRAM address. We'll just type vload as our macro. And so VRAM address is 2000, so we just type in vload 2000. And then the source is bonkbg, so bonkbg. And the number of words down here, where's that? Right here. So 1000. Okay, so VRAM address, location, and size. I think we can now delete all of this. Okay, and with that done, let's load in the font and sprite graphics too. So down here at the label we have my font and sprite characters. I'll just address it by my font, and then we can load in the sprite characters from the same bank. So we don't need to map that twice. Font. Okay. And so same thing, vload. I think I'll put the font in VRAM address 1000 because from 000 that's our BAT address. That's where our tile map will be, and probably a little bit after the tile map we can have our sprite definition table. That'll go there, and then after that it can just be graphics. So from 1000 it'll be graphics. My font, and the size of my font, it was half of what the background was, so hex 800 words. And our sprites I will shove at VRAM 3000. Sprite characters, and the size of that, well, we can double check by looking, but one 32 by 32 pixel sprite is hex 100 words. So we have two of them, so that's 200 words. Okay, so just try to remember that. A 32 by 32 sized sprite is 100 words big, or hex 200 bytes big, and we have two of them, so there we go. We'll load those two sprites in first, and maybe I'll comment that. 2 32 sprites. There we go. I don't think we need to comment this. We understand the background and font. So hopefully that'll assemble fine. Oops, one. So assemble that, and run the PCEngine file. It should look okay. And so let's see, where's the font? Yeah, the font, well, the colors are not set at all yet, but the font is loaded into VRAM at address 1000. And then from 2000 to 2FFF, it's the bonk background, and then later, here is our sprites, but we'll go to sprite view, so sprites. Here they are. Okay, so we can see it's the top half of bonk, and then it's the top half of the cheekgun, then it's the bottom half of bonk, and the bottom half of the cheekgun. So our sprites are loaded into address VRAM address 3000. And so that works just fine. So we got our graphics loaded into VRAM, but as you probably noticed, the background colors, the palettes for each of these images was not loaded in. And that's, of course, completely natural. We have to load in the graphics into VRAM first, and then the palettes also have to be loaded into the palette RAM manually. We have to do that ourselves. And so each of our pictures that we're including has a single index, a 16-color palette entry. So we need to load those in. And so we'll be using the macro set bgpal, and we can also use set sprpal. But we also need to include those palettes from each of the PCX files. So we have some space left over in this bank. So that's what I'll do. I'll call it font pal for the font. And so we write incpal, and we just call the same name as, or we include this from the same PCX file, and it'll include the palette. It'll do this, and it'll probably include all palettes in the entire PCX file, but if you don't want that, you just want to do a single one, so we do start at palette index 0, so each 16 palette, 16 color chunk. So start at palette 0 and import only 1. So that should include from the first 16 color palette entry, and only do one of them. And so next we'll have the bonk pal. And that's probably, where was that? Down here. So we include the palette from the bonk background. And last will be the sprite palette. Those bonk sprites. Spacing doesn't matter, but there we go. I'll just include that too. So incpal and from this PCX file. So that'll add several more bytes to after the graphics in our file. So a single palette entry is 16 colors, and that's one word each. So that's 32 bytes. Another 64 bytes, and I think that's what, 96 bytes. If my math is good or bad. All right, so I'll add like 100 or so bytes for 3 palette entries. And then, so we'll use this set bgpal macro up here. After loading in the graphics, it's still in the myfont bank, right? So we have to remember what bank we're in every time we do loading and saving the graphics. So let's see, we've included the font palette and then the background palette right after each other. So yeah, the font and bonk palette. So we can just copy both of those at the same time, and then do the sprite palette later, or after that. So set bgpal, and space, kind of a big space. Set bgpal 0, and with font pal, and then I think we just type 2, and that will do 2 of those indexes, palette indexes. So set sprite pal, also 0. And so probably have to do 1, just like that. And maybe we do literal to literal 1. So I think we should compile that or assemble that and see how it looks. So assemble that and run that. So but we still don't see anything on screen because it's just in VRAM. It's just been loaded in VRAM. So our font palette looks fine. The background color is still green because of our code that changes it. And the next palette index 1, yeah, it looks fine. See, no problems. And then sprites are there. So we'll go with the sprites. And sprite index 0 is also fine. Bonk and the chicken look fine. No, colors are fine. One other thing, I think I'm going to change those background colors just a little bit to make them a bit more pleasing to the eye, at least while we're testing stuff. So in the VSync code, I'm going to change the background to black, actually. So here will be a black background. And I think in my HSync code, I'm going to change some stuff too. I'm going to change the background here to gray. So instead of green showing up everywhere, I'm going to have it, black and dark gray. Gray. And so that's in my macros. I've already made macros called background color gray, gray 1, gray 2, I think. There. So now our font shows up a bit better. We'll have our background be black most of the time, maybe, and so we can have the font readable just for our display, output display, and the sprites will be against the black background. Or we can change the color since their outline is nearly black anyway. So that's our next step, get all these graphics on the screen.